Hello everyone, this is the senior design presentation of Group 18. Our project is the Rain Energy Harvester.
Hi, my name is Evan Main.
Hello, my name is Carlos Molina.
My name is Alexander Rutherford.
And my name is Rayon Baig.
The main concept of our project is to design a device that will be connected to a single gutter of a home and use the rainwater to generate power using a hydroelectric turbine and motor. While the turbine is rotating, the energy generated will be used to power a small external device like an LED light. This device can act as a supplemental source of renewable energy for large office buildings, shopping malls, and small residences. For this project, we wanted to create a sustainable solution for energy generation while contributing to the preservation of the environment and while taking advantage of a natural source of energy that is currently not utilized. The goals of this project are that the device will be capable of generating energy using the rainwater flowing through a single gutter, effectively turning the rainwater into a renewable source of energy that can easily be installed on a common house. The energy generated will be used to power an external device while displaying the data about the power statistics like voltage and current. The specific objectives include to convert mechanical energy to electrical energy using a Pelton turbine and a stepper motor to power an external device. Use wood with a water-resistant sealant and plexiglass material for the turbine and electrical casings to prevent water damage and also for demonstration purposes. And the sensors will be used to gather data to display on the LCD screen. Now let's see the engineering specifications of this project. The three main specifications we're going to demo are the turbine speed, the power generated coming from the motor, and the output power coming from the USB outlet. These three specifications will be calculated from the data gathered from the sensors and will be displayed on the LCD screen. The minimum turbine speed that we're expecting is 120 RPM, but based on the testing we have done so far, the turbine stays consistently in the range of 180 to 240 RPM using the pipe structure. The minimum power the motor is expected to produce is 0.25 watts, which equals to a minimum for output power of zero point 0.1 watts. Regulation efficiency is another specification that we can show during the final demo as a backup. To maintain system performance, the regulation efficiency for all loads and output devices must be higher than 50%. We're expecting that the temperature inside of this device will stay in the range between 5 to 35 degrees Celsius, which will keep the water from becoming frozen and the electronic components from getting damaged. We're expecting water flow rates to be between 2 gallons per minute up to 6 gallons per minute. The dimensions of this project is expected to be approximately 1.5 meters by 1.5 meters by 2.75 meters.
Here is our hardware diagram. Water flows into the top of the piping structure, filling it over time. The water is forced out through a jet nozzle at the base of the pipes, into the paddles of the Pelton turbine, and out through the open bottom of the turbine chamber. This causes the turbine to rotate, which will drive the motor through the mechanical connections, generating an AC signal which will be converted to DC using two full bridge rectifiers in series. This DC signal will be measured by the first shunt sensor. Then the signal will pass through a voltage regulator and will be measured by the second sensor at the outlet of the system. A regulated 9-volt battery will be used to power the microcontroller, the sensors, and the LCD screen. These components are only used for monitoring the generated signal and are not needed for power generation. Here is the 10-foot tall PVC piping structure and the jet nozzle interacting with the hydropower turbine. The casing for our prototype will separate and house the water turbine and the electrical components. The casing is made from pressure-treated pine wood and had multiple clear coats applied to further increase its resistance to water damage. The main types of hydroelectric turbines that were considered were the Turgo and Pelton turbines, as these types were best suited for the water head levels and flow rates that we expected. Ultimately, the Pelton turbine type was chosen due to its higher efficiency ratings and lower flow rate requirements. Several Pelton models were compared, and we selected the model that had the highest number of adjustable paddles with the highest runner diameter. We knew that we could reduce the runner size later if it was too large, and that we could adjust or even replace the paddles if the original paddles underperformed. When determining what microcontroller unit to use, we used the following factors to make our selection. The I2C peripherals would share the same 2 data pins, while the SPI peripheral would need 4 to 5 data pins. This means that very few data pins are actually needed for the project. So while a higher pin count can allow for later additions, it isn't necessary. This project is more hardware focused, and only basic functions and calculations will be handled by the MCU. So the bit count, the memory, and the clock frequency are less important as a result. The MCU and its peripherals will be powered by a battery, so the operating voltage, power consumption, and low power modes were all considered. Group members were already familiar with and owned the Arduino Uno and the MSP430 models, so these were considered immediately. Ultimately, we decided that the Arduino Uno and the ATmega 328P microchip would be the best fit for our project, as the advantages the other models had over it were either not important enough or too costly to justify.
The motor for the project is responsible for converting mechanical energy to electrical energy when the turbine is rotating. For this purpose, the criteria for the types of motors were chosen for a motor being used as a generator. The criteria included cost, shaft smoothness, complication, and efficiency. The shaft smoothness and efficiency were important for the usability of the motor because of the estimated 2 gallons per minute water input to the system. The low input would mean less force available to spin the motor and a low amount of energy able to convert to electrical. Hence, the shaft being easy to spin and conversion efficiency being high was important. Each motor had a different complication when it came to integrating the motor to the system, and less complicated motors were sought for if other criteria were not being sacrificed. Ultimately, the stepper motor was chosen for the design of the project. The stepper motor was on par on efficiency compared to most of the other motors, while being inexpensive, easy to rotate, and easy to integrate to the design. The only complication for the stepper motor was the need to change the output to AC to DC by full bridge rectifiers. 2 variations of the NEMA 17 motors, as well as the NEMA 23 motors, were compared when selecting the part for the project. The goal when comparing the motors was to select the motor that can output the most suitable voltage and current values for small-scale devices. While any of the motors would work for the design, we determined that the NEMA 17, 17ME15 was the best for the project. The motor had the most steps compared to the other motors, and the max voltage was relatively high, at 73 volts, resulting in a potential increase in voltage and current output than the other motors. With the potential to increase output and the cost being on the lower end of $16.99, the NEMA 17 17ME15 stepper motor was selected for the project. The voltage regulators will be used to step down the voltage from the battery to microcontroller and to step down the output voltage of the motor. There were 2 types of voltage regulators researched, the switching regulators and the linear regulators. The switching regulators can step down, step up, or do both, and was rated with high efficiency and heat resistant. The linear regulators can only step down voltage, but is simpler to design and less expensive. While originally a linear regulator was chosen, Dr. Chan recommended using a switching regulator instead, and with the project generating low amounts of power, higher efficiency was important. Hence, a switching regulator was chosen. 3 different switching regulators were compared, with criteria being cost, efficiency, voltage input, voltage output, current output, and size. Dr. Weeks has recommended us to use the LM2576 switching regulator, with the voltage input being 4 to 40 volts, voltage output at an adjustable 3.3 to 37 volts, and max current at 3 amps, the regulator was adequate to drop down the voltage for both the MCU and the system output. On Weebench, the efficiency of the buck converter circuit design with the regulator was rated at 83.4%, being highly efficient for the project. The size being larger than the other regulators was very important because the LM2576 was large enough for breadboard testing and soldering on the PCB. The other two regulators were too small to be tested on the breadboards, requiring them to be soldered onto the PCB without being tested. We made the mistake of using the LV2862 on the PCB and realizing the regulator was not working properly after being soldered. Ultimately, the LM2576 was selected for the project design, providing reliability by testing and having operable criteria values to step down voltage for the project. The battery will be used as the power supply for the microcontroller. The battery chemistry and size were compared to pick the most suitable battery for the design. The chemistry was chosen to be alkaline and the size was chosen to be 9 volts. Alkaline was chosen because it was commonly sold around stores and its capacity was high without being too expensive. Knowing the power supply was only going to be on when the user wanted the display status, sacrificing some capacity to save costs was well worth it. The 9-volt size was chosen because the battery in the project will run at recommended levels to the microcontroller. The 9-volt battery size allows of only needing one cell to reach recommended levels, then the alternative of needing multiple cells if other battery sizes were chosen, making the project design simpler and cleaner with the 9-volt size. 3 different batteries were compared when deciding the one to use for the design. The MN1604 was chosen to be the battery of the design. The capacity and durations were similar, and the cost may appear to be higher than the other batteries. The battery was available in store, which avoided delivery fee, therefore was chosen.
For this project, we consider different types of displays and panels, which include the twisted pneumatic displays, in-panel switching panels, vertical alignment panels, thin film transistors, and OLED displays. Our screen needs to be able to display text and a graph with high resolution and refresh rates, while providing the same display performance across different viewing angles. Response times refer to the time it takes the screen to change from one color to another, which determines how fast the screen can update. The TFT and OLED displays were great options for our project. However, the TFT displays on average consume significantly less power over time than the OLED displays. OLED displays with significant screen size are also more expensive than the TFT displays with the same screen size. Ultimately, we chose the TFT screen as our display. Another consideration for this display was the screen size. Some of these displays technologies are used for larger applications like TV screens. Several models of the other display types did not meet all of our display criteria, while most TFT screens met these requirements. When making our screen selection, we also considered some OLED displays that could have worked in our project. However, we ultimately decided to use the bigger screen size with higher resolution of the Adafruit TFT ILI 9341. This display has a resolution of 320 by 240 pixels, which is more than enough to display the data with high image quality. It uses SPI as its interface, which is what we were aiming for. This is because SPI have a higher data transmission speed between the MCU to the display than the I2C interface. We needed this higher refresh rate to ensure that the graph of power over time was going to update accurately and in real time. For the voltage and current sensor, we considered different methods that accurately measured these two values, and we selected the method that was the most appropriate for our project. The sensors that use the Hall effect principle or the induction method mainly added an additional layer of complexity for our specific application. These two methods would have required additional components to guarantee accurate readings such as a current clamp. The Hall effect and induction type sensors also provide accurate readings for voltage and current, but due to their dependency on external factors like relying on a consistently strong magnetic field for the Hall effect or changes in humidity levels for the induction type, we decided to use the shunt-based method. Even though it is an invasive method for measuring, this drawback can be mitigated by using low resistance shunts, which are resistors with very low resistance. For the sensor selection, we consider sensors that only read voltage and current, as well as some alternatives that can measure both. Since our objective is to accurately measure the power generated and we need to measure the power from the motor and from the output outlet for the external device, we selected the INA226 sensor that can measure voltage, current, and power with high accuracy. This sensor can measure voltage from 0 to 36 volts and current from 0.5 milliamps to 50 amps with 16 bits of resolution. We're also aiming for a sensor that will use I2C interface because we needed two power readings, which meant to have two peripheral devices. Since this sensor uses I2C, then we can simplify the number of connections for both sensors.
The shunt sensors had address pins that were either connected to VCC or ground to assign an address. The 4-wire SPI option was chosen over the 8-bit parallel option, as the improved speed offered by the 8-bit option was not necessary for this project. The ATmega 328P has dual inline packaging, which allows us to use a socket that the MCU can be inserted into instead of directly soldering the MCU onto the PCB. This gives us more freedom when choosing how to program the MCU and allows for easy replacement and testing of this component. An FTDI adapter is used to program the MCU while connected to the PCB using UART communication protocols. Here are the mechanical components in our project. These parts will be used to connect the turbine and the motor.
So here is the overall PCB schematic, which includes two voltage regulators, a full bridge rectifier, an MCU, and two voltage and current sensors. And here we have our AC to DC conversion circuit. The circuit takes the AC input from the motor and converts to DC using two full bridge rectifiers in series and outputting this into sensor 1. Here's the first sensor, which is powered by the supply voltage regulator, and the power generated by the motor flows through this to the output voltage regulator. Here's our output voltage regulator, which takes the voltage from sensor 1 and regulates it down to 5 volts while attempting to maintain the same power. The current then goes from this regulator to sensor 2. And here's sensor 2, which measures the voltage and current right before the final output. And it is pretty much the same as sensor 1, besides its position in the PCB. So in our PCB, we decided to include two outputs, one to connect to a USB breakout board, and the other would just be a DC connection. Here's our supply voltage regulator, which powers the sensors, LCD screen, and MCU by stepping down a 9-volt battery to 5 volts. And here are the MCU connections. We used an ATmega 328PU, and we included a FTDI pin header to easily reprogram the MCU as shown on the left. We also included a crystal called Q1 in the bottom left of the board to help the MCU start up. And we also added an LED to demonstrate that the MCU is functioning. And in the bottom right, we've got the LCD connections. Here's our final PCB board layout, which shows how we placed all the components.
Here is our software diagram. First, the sensors in the LCD pins are configured. Then measurements are taken using the first sensor, and unit conversions and calculations using these measurements are performed. program then branches off depending on what mode prototype is currently set to. This can be changed by the user at any time by pressing the LCD's interrupt toggle button. Mode 1 is used for displaying the measured values on the LCD screen in text form. The power measured by the second sensor is used to determine if the outlet is being used. If the power is below detection threshold, the regulator efficiency reading will instead display an idle USB message. Next, text labels and units are displayed on the screen. And finally, values measuring both the sensors are displayed on the screen. These values refresh every second. Mode 2 is designed to display to the user the power generated by the turbine using a line graph. The y-axis is power in watts, and the x-axis is time in seconds. First, both axes are printed onto the screen. Then, power measured by the first sensor is displayed as a line each second. After 30 seconds, the graph is cleared and the process restarts. For the IDE, we considered using the Arduino IDE, Code Composer Studio, and Visual Code Studio. The Arduino IDE was chosen due to its compatibility with the MCU we chose, group members' familiarity with this IDE, the large amount of available support, and the numerous GitHub libraries available in its library manager. Python and C++ programming languages were the two languages that were really considered for use in this project. Ultimately, C++ was chosen over Python due to group members' lack of experience with Python and the greater low-level control and memory optimization options afforded by C++. Some of the libraries that we are calling functions from are listed below. The image on the left shows the text mode, and the image on the right shows the graph mode that were mentioned before. The toggle button will be placed to the right of the LCD screen and will allow the user to change between these modes. The outlet and two switches will be located below the LCD screen. One will turn the outlet on or off, and the other will be used to turn on and off the prototype itself.
This is our project timeline, and we expected to be finished with our overall project by April 1st, but we found that it took one more week than we initially expected. Here is our work distribution table, which shows what each person has done. And here's our bill of materials table. So the mechanical parts, which we ordered from the machine shop at UCF, we received for free due to funding, which was also provided by UCF. And this included the turbine shaft, gears, and bearing. We also managed to get our switching regulators, the LM2576, for free as well, since UCF has them readily available for students. So in total, our cost came out to be $363.53. In terms of challenges we faced, the casing and mechanical parts were the most difficult since we don't have much experience in that area, so we sought out help. We also found that we needed to be more precise with our PCB component placement, but even after fixing most of the issues, we've got one small issue where some current is induced where it shouldn't be. Another thing is that we thought our PCB sensors were a bit off, but afterwards we realized they just need to be calibrated. Also, in terms of the budget, we thought we would have issues staying under $400, but we received some funding from UCF, which helped. Thank you.